How are you?
Good, how are you?
Okay. Yeah, I don't know what's going on with the Jitsi meeting spot.
Yeah, just it's weird.
Well, anyways, I guess, yeah, both of you have seen the slides, so.
They look good.
Yeah. Share the screen here. Great. Can you see the slides?
Yes.
Okay. So I guess I can go over them, go through them, and then we can ask questions at the end. We put it in presentation mode, and then at the end we'll do like a Q&A about it. Hello, this talk is called Developmental Embodied Agents as Metabrain Models. My name is Bradley Alicia, and this is an effort with about 6 other people, including Stefan Dvoretsky, Zhi Gong, Ankit Gupta, Sam Felder, and Jesse Parent. We're basing this concept let me start over. I've done this like a couple times, and every time I record, I always manage to trip up over the. Just have to get a good way of going here. Let me start over. Hello, this talk is called Developmental Embodied Agents as Metabrain Models. I'm going to be presenting this work. My name is Bradley Alicia, and I'm presenting with about 6 other people: Stefan Dvoretsky, Zhi Gong, Ankit Gupta, Sam Felder, and Jesse Parent. Actually, it's 5 other people. Okay, let me do it over. Hello, this talk is called Developmental Embodied Agents as Metabrain Models. My name is Bradley Alicia, and I'm presenting this work with 5 other people: Stefan Dvoretsky, Zhi Gong, Ankit Gupta, Sam Felder, and Jesse Parent. Our work is based on this larger concept called the metabrain model. And so a metabrain model is something that we've been developing over time, and basically it's 2 different models: a hybrid model, where one part of the hybrid model is representation free, which means that it relies solely on the structure in the empirical world. And then examples of that include Bradenburg vehicles and neural networks. And then there's a component that's representation rich, and that could be any sort of like highly symbolic model. So something that maps the empirical world to a set of signs or interpretive criteria. And the way we have it here is that they're stacked on top of one another, but as you'll see, there are a number of ways that those things can be integrated. So our representation-free layer will be represented by Bradenburg vehicles. And for those of you who aren't aware, these are Bradenburg vehicles. These are vehicles 2A and 2B. These are first-order stimulus response mappings. So we take in information about the empirical world, the sun up in the sky, and the vehicle takes it in, and it elicits some sort of behavior by the vehicle. So you observe the empirical world, and there's a hardwired system within the vehicle to elicit a response. The vehicle yields behaviors that resemble taxis or the sort of reflexive behaviors that we know about from ethology. These are very simple neural networks that are embodied agents. So what's inside of the vehicle is a very simple neural network that maps the sensor to the effector. We've gone a step further and developed these things called developmental Bradenburg vehicles, or DBVs, and they can be achieved in a number of ways. And so in this paper, we talk about two of those ways. But one thing that unifies them is this key component of connectivity activation encoding. And so this WIJ is this connectivity matrix. And so the idea is to take this connectivity matrix is to expand or prune the number of connections, mostly expand, but you could also prune them. And you're looking at increasing or decreasing the size of IJ, or increasing or decreasing the values in IJ. And so we've done this in two ways in the paper. We've mentioned Hebbian learning, which is where a matrix is modified using a sort of a wire together, fire together rule. And this creates viable spatially explicit multimodal associations. We'll see how that works in a minute. And then we use genetic algorithms. So with genetic algorithms, we create mass topological reordering of that network within the Bradenburg vehicle. And we select viable matrices through mutation, recombination, plus some fitness function that is reflected in the behavior of the robot or of the agent. So this is an example of a sort of an early developmental Bradenburg vehicle. We have the sensors up here. We have the effectors down here, which are wheels. We have these internal nodes. And you can see that we've integrated this CGS kernel into this network, and we'll talk about what that is in a minute. But right now we have these internal nodes that are sort of pass-throughs for senses. So for example, this one here integrates all of these sensors and then passes that signal down to this kernel. This node here takes information from this sensor, passes it down to a number of intermediate nodes, and then out to the edge, which is this effector node down here. So it's a simple mapping, but it becomes more convoluted over time. The internal nodes mediate between sensor and effector and can combine sensory signals, among other things. And we're using this power of layered processing, which we know very well from deep learning now, to do this work. And so this is an example of a more advanced developmental Bradenburg vehicle, more connections, a couple of other nodes additionally, and we still have the CGS kernel, of course, and we'll talk about that in a minute. But basically, in this advanced version, or this more developed version, we have more nodes, more convolution of the signal across 3 different layers, internal layers. So we can grow DBV brains, like I said, in 2 ways. This is the first way, this is actually the genetic algorithm that we used. So in this case, the vehicles interact in a world. So if you see in this figure, the vehicles interact here, and their behaviors here define a fitness function. This allows us to generate embodied topologies here, which have these sensor nodes, these effector nodes, and these internal nodes. And the connections between them are defined by that matrix and manipulations of that matrix. And then finally, we're using a genetic algorithm and the fitness function to generate new topologies and evaluate them. So other rudimentary behaviors characterized as love, aggression, or happiness are possible. So I talked about earlier about the taxis, but those result from the hardwired versions. The developmental versions generate other behaviors or mediate those behaviors. It's important to realize that when Bradenburg wrote his book and described these behaviors, that he described them as like love and aggression and happiness. These behaviors look like emotional affinities, but maybe they're not. Maybe there's something else. And so how do we achieve richer and more robust symbolic behaviors? So one step in this direction is the other way that we're generating these developmental Bradenburg vehicles, and that is contextual integration. And in this case, this is the Hebbian learning example. And in this case, we're taking 2 distinct sensory inputs, odor and taste, and we're associating them in some way, and we're establishing associative learning. And so you can see here, this is a diagram of the associative learning that goes on. There are a lot of details to how this is carried out. But basically, this generates a behavioral signal that integrates these two sensory inputs and results in a behavior that is adaptive. And so associative learning is the basis for developmental plasticity in this case. Another way we can do this is through something called chromotaxis. And chromotaxis are like phototaxis, if you're familiar with that, where the agent either is repulsed from a light source or attracted to a light source. In chromotaxis, our agent will be attracted to a specific color. And so there's a preference for colors maybe linked to emotional valence or something like that. But this is a little bit more advanced than phototaxis. And so one way that what we need to do in the agent to create this behavior is to create a cultural representation. And so and this is what we call it, a cultural representation. We'll talk about why that is in a minute. But what will happen here is that the agent will sample the color space at different points. And you can see at the right that they're sampling in these different color blocks. And they're sampling an RGB space, basically. So they're sampling these colors, but they're also building a representation of this RGB space. And they're doing so by sampling the natural range of color components in that color channel. So when they're sampling, say, these 2 points, they come out with, or I think they sample a couple other points in this example, but they come out with this distribution of parts of the color channel. So they've sampled, in this case, they've sampled a lot of the very lower end of the red color channel and maybe one point in the middle of the color channel. So they build these representations that are cultural, meaning that they can take these limited samples of the empirical space and build some meaning around it and then share that with other agents. So the thing that we use for the cultural representation and the thing that's our representationally rich component of this metabrain model is the CGS model, or the Contextual Geometric Structures model. And I presented on this at Alife about 8 years ago, so this is the reference. And there are a couple of parts to this. One is that this is a soft classificatory kernel, so it's based on fuzzy logic. It's the idea that you have these membership functions and that they combine in some way to give you a representation. So, for example, in our case, if we build like a simple continuum of light and dark, and we want to sample something halfway between light and dark, that representation will yield two membership functions, one that is 50% light and one that's 50% dark. And that will give us attributes of both ends of that continuum, as well as other components that we want to add on to that. This is based on a structuralist view of culture. So cultural relationships in the structuralist view are a series of overarching structures. So they kind of mediate behavior, but we don't really think about them much. They're sort of, beyond sort of the way, sort of outside of our direct cognitive experience. Structures are the key to cultural representation. So if these representations, if agents want to share these representations between each other, then structures are key to that relationship. And in humans, cultural structures are built on the basis of nature, kinship, and the ritual world. And so this leads us to these conceptual automata. So this is actually inspired by the concept of the habitus by Pierre Bourdieu. It's these durable, transposable dispositions that are generative and organized practice and representations adaptively. And so that's a lot of words, but basically the computational objective is to build a scheme that transforms physical phenomena into operations that can be compared in an evolutionary context. And so how do we represent sensory information to perform these cultural operations, to build these higher level symbols that can be shared? We build these n-tuple surfaces that allow us to combine all possible combinations of things. So if we have this object, we can represent it as a series of binary oppositions or as some sort of geometric space, and then we can label those things with endpoints or reference points, and then we can build these classifications, these membership functions that tell us to what degree this phenomenon in question belongs to this concept. And so again, these soft fuzzy classifications are a little bit different than probabilities. They do not require transitivity, distributivity, or symmetry. And so these are examples of those things. And notably, it's not like, so we can represent things and have multiple representations generated for a single sample or a single classification. And then this is an example of one of these CGS structures. So I haven't really shown you these things. They're very good. You can do very good visualization with them. They are more conceptual, but we have written code for it. But this is an example that I'll walk you through. So this is an example of our RGB color space represented as a contextual geometric structure. Like I said, we build 3 binary representations of R, G, and B. So this gives us these 3 corners of each of these colors are a corner of a triangle in this case. And so as we can see, we can have at least 3 membership functions. We can specify a lot of this sort of, depending on the simulation that we're running. So we have this R, this G, and this B. So if you're belong to this G membership function, an increase in green in this color will increase your membership in this G. If you belong to the B membership function, it increases your membership in B. And if you belong to the R membership function, it increases your representation in R, or your membership in R. And so this representation is also developmental because it allows us to maybe, specify more parameters later in development and then connect back to that Bratenberg vehicle as it's sampling the environment. We also can build other types of representations. So in this case, down at the lower right in C, actually let me go to B and then C, we have this transition from a square which has 4 sides to a circle which, if you take a square and you recursively cut the corners, you end up with a circle over many iterations. And so we'll just call it a 4,000-sided square. And so this creates this continuum, this polygonal continuum, that your object can belong to. So you can have membership in square or membership in circle, or this sort of membership in circle based on how dissimilar it is from a square. And so you can actually create these membership functions and create things, and you can refine it over the course of development. So we can create a continuum that is very coarse-grained. So it might be from, our circle might end up being like a octagon, right? So we only go from 4 to 8 sides. And so that's something that's pretty easy to classify, and a very young Bratenberg vehicle might be able to do that. But as the Bratenberg vehicle matures with more internal nodes, we might give it a circle as its endpoint. And so then it's classifying everything from a square to a circle and building a unified representation of that. So the future directions, so where do we want to go from here? We've done some work on cumulative behavior already. So, going between agents, not just in a single agent, we've used these hardwired Bratenberg vehicles. We've trained them on images. And this is actually the work of Ankit Gupta, mainly. And he's been doing this thing with training them on images. So he has an image that you would train it on, and it's either repulsed by the image or it's attracted to the image. But they do this in a collective way. And I'm hesitant to call it collective behavior because they don't really communicate. They just kind of do it on their own and generate these swarms and patterns in this, as you can see in the screenshot. But we have other ways of doing this too. One thing we want to do in the future is integrate model types better. So we're dealing with these hybrid models. So how are these developmental Bratenberg vehicles and these contextual geometric structures integrated? Are they integrated as layers or parallel systems? I showed you in the example here, they're in a layer, but they're also parallel systems. We can also do this in terms of layers like an onion, or like actually what you see in the brain, which is where you have one layer over the top of the other. So every Bradenburg vehicle node would communicate independently with the CGS in that case. And that might yield a lot different results. And so then I just showed you the example of cumulative and collective behavior. And then there are alternatives. We talked about in the first slide about this generalized metabrain. What are the alternatives to, say, DBVs or CGSs in those cases? We should note that developmental Bradenburg vehicles are representationally sparse, but they're embodied. So the one advantage of using Bradenburg vehicles is that they're these embodied things, and so we can leverage that advantage in this metabrain model. But could you use some other type of model, like embodied deep learning or developmentally inspired agent-based model? We could do that. We don't know. We haven't investigated that. We also notice that CGS are representationally rich but limited in scope. So these models, I wouldn't say that they're brittle, but that they're good for a certain thing. And we could use other types of models such as ideological modeling or cultural algorithms, and they might work better, or they might give you they might be suitable for another application. So thank you for your attention. Our group is Representational Brains and Phenotypes. You might want to attend our Saturday morning NeuroSim meetings. Those are open to the public. Thank you to Google Summer of Code in 2018 and 2019 for pushing this project forward. And then you can check out our GitHub repo, our metabrain models, at our lab GitHub. And there's the link. Thank you for your attention. All right, I think it was a little long, but that's okay.
That's great.
Yeah, thanks.
Yeah, I think that was probably that really incorporated a lot of the things well, and I think it makes sense in terms of how contextual geometric structures is kind of situated relative to the work of Bradenburg vehicles, and I really like I know it's easier because we've been in it and I've been focusing on it, but seeing the way the representation and non-representation are trying to be put together in this fashion, I think is one of it's my favorite presentation about this so far that we've done. But,
yeah, usually if you present a couple times on something, you get you get more examples, you're thinking about it more. I mean, I've presented before, but it's always good to have a new presentation on it because you can shuffle things around and think about it.
is there, I don't know if we're currently acting like we should be addressing potential viewers or just discussing amongst ourselves things right here.
We can talk about, just any questions you have.
For the big learning, I think you can, when you're mentioning odor and taste, you can just briefly talk about the distribution of odor and taste, the lower right graph. The odor is more distributed in a space and taste, so that's just distributed. So that people will understand why we choose odor and taste. That's just analog.
Yeah.
Yeah, like the Bradenburg vehicle is trying to use the association to learn the variable with more spread to infer the variable with less spread, because the Bradenburg vehicle is less likely to in contact with the variable that is with less spread in space. So that the Bradenburg can use the inference to change its motion.
They're differently distributed in space, or?
Right, they're unevenly distributed in space.
Okay.
So that the Bradenburg will learn association and use the association to infer one variable from the other. So that render variable can, control this factor to change its motion according to the inference.
Okay.
And in kind of where some things are going currently, and some discussions that I've been looking into, I think it's a really interesting example in terms of thinking better in terms of affordances, because these have these different skills or awarenesses, or in this case the senses, having different spreads relating to each other, but it's sort of modifying how the agent has these different skills or abilities, and putting the two together, sort of combining like these if not skills, like capacities for behavior that affect the relative niche that has the ability to interact with the environment. So as it gets better at coupling the two senses, it's like, it's ability to have a clear comprehension of not only the environment, but how it could interact with it, in the sense of it now has the ability to take even more process, or however you would like to say, even more information, because it has higher capacity, not just this associated senses, but also this combined, the combination of these, and I think this is where you kind of get to wonder, okay, well, what could this lead to when you start adding more representational layers? Like, how will this fall into a more advanced, representational layer down the road too? Like, okay, as it's learning, what are the associations that it gets to make with these enhanced ability to process information, as opposed to just these disparate, sensory inputs? I think that's a really interesting trajectory of things.
Yeah. Okay. Well, thanks for coming to the talk. I'll put up a recording, and then I guess they're going to have it available to the group, like all throughout the conference, and then the workshop is actually next Saturday, and I guess I'm going to be the representative for us, and it's just like question and answer. So this will be helpful too, our discussion for that part. I don't know how it's going to be, like 2 hours, but it's going to be like on Zoom. But people will have seen the video before they come to the session.
I'm not sure if they see our comments, but thanks for watching. And
yeah.
Check out our lab and materials if you're still inclined. Thank you.
Yeah.
Actually, I have a question about the triangle representation of the it's just like slide 16, 17, 8. Like, what is actually I am not that clear about the visualization of the 3 tuple. It's triangle in a 3-dimensional space.
Yeah, it's the let's see if I can share my screen again. It's up here.
Yeah, right.
16, yeah.
It's like a cylinder.
Yeah. So, the RGB representation is this one face of this, and then this side is the polygon. So the idea is that you have this color representation and the polygon representation on this side, and the rest of these sides are redundant, but that they're linked somehow between the polygon circle and this RGB representation. And so there's like a space inside of it that's, where they can interact. So there's a value in the RGB space depending on your color. And if you go back from this front, you have the polygon circle, and that goes back, and there's something in the middle. There's a point that is a representation of the two of them. So the idea would be like, if you have in this polygon to circle, you have an octagon. The octagon would be maybe, up here, and that would go into the middle, and then you'd have a color here, and that would go meet into the middle, and you draw a line, and that would be your point. But you can configure these in different ways, so you can, the representation, you might encounter other things other than polygons. So you might have something that's 20 or 30 sided. It's kind of like a circle. It would be maybe further down this side, and then it would come out here. And so you could draw like distances between different objects, and you can generate a distance and generate, some sort of representation. I mean, kind of like when we think about the relationship between objects. So it's like if I have a vase and I have like a cup, they're two different things, but they look similar. They have some similar attributes, and they also may be different colors. What are the similarities and what are the differences there? So we do some mental calculations, but at the end of the day, we have to have a representation, and people will debate about this. You have to have a representation of each thing, and maybe of the color, but you also have to know that there's a relationship between them. Otherwise, we just say this is a vase, this is a cup. I don't, it might be like you might not be able to map between them. And so that's kind of
were you going to say something more?
Go ahead. No, go ahead.
Oh, I was going to say, so it's sort of like each side of, I don't know how to really say, you start with a triangle face of the polygon or the contextual structure, and each face would represent a different spectrum or gradient within which you could have. Like, and on the side that was the square in this case, that was, I guess, the spectrum from square to circle. But you could potentially have another one that would represent, like some other feature, like maybe opacity or whatever. And the more faces you would have to the geometric structure, the more information or that you can represent in that way. Is that essentially what it's getting at?
Yeah. I mean, it's the sort of the meaning or the associations would be generative, because you'd have like you'd sample a bunch of things, like the shape and then the color, and then you'd have a bunch of points, and they'd intersect somewhere inside the structure, and then you could also draw differences between those intersections, and then you could get like a sort of a map of how, like say color maps onto shape, and then how those things are related in your experience.
I don't know if that was in the slides, but I know like some of our CGS slides have the sort of Venn diagram looking spaces in them.
Yeah.
That would map the yeah.
Yeah.
So a metaphor of it is more like a control panel, right?
Yeah. All right. Any other questions?
I think that's all for me.
All right. Well, thanks again for attending, and
Thank you.
yeah. Talk to you guys later.
Bye.
Bye.